anyway, yeah, guys, welcome, and glad you could see the practical side of vapor phase magnetometry by atomic physics. I want to emphasize that this is not a research system that Peter has at Sandia. This is an educational system that happens to be made as one of the products by TeachSpin Incorporated, whose mission is not to do research, but to provide apparatus that, say, upper-level physics undergraduates might encounter in an advanced lab course. So that's why it's open frame, and it's because it's TeachSpin, it's got to have some wood theme in it. And the attention we pay in here is to very careful control of magnetic fields. And in this case, we have actually the ability to work not in a quadruply shielded magnetic environment with femtotesla sensitivity, but in the open air, in ambient magnetic fields. In fact, in dim light like this, we don't even have to put a black cloth over it for it to work. So for orientation here, you're welcome to take one of these blurbs, the sales brochure, so to speak. But the physics requirements are on a single-page handout here, and the physics possibilities, or some of them, are on the two-page handout. And there's my business card if you want to check in with me later. But yeah, in brief, right, it's all done with alkali metal atoms. In this case, for technical convenience, the atom of choice is rubidium. So deep inside this little oven structure is a little glass-walled cylinder, an inch in diameter and an inch long, and in it is a bit of metallic rubidium, and the whole thing inside the plastic here is temperature controlled to 50 Celsius, just to raise the rubidium vapor pressure to a level where there's a fair fraction of light at the right wavelength passing through that'll get absorbed. That's where we do the pumping. In fact, to be exactly technical about it, we pump in angular momentum into that light, into those atoms, by using circularly polarized light.
What's the method with which we are cooling that to 50 Kelvin?
Heating is 50 Celsius.
50 Celsius.
That's right. It's just plain resistive heating.
You want to vapor,
Also
right?
like
Yeah.
some kind of Doppler cooling or something.
Nope, nothing exotic.
Vapor is heat up.
Yep, that's right. Yep. One other distinction compared to a research system is that the light is the so-called D1 wavelength that elevates ground state rubidium atoms to their very lowest excited state. And it's done at about 795 nanometers, which could be done by a laser. But in this case, we have an old-fashioned discharge lamp, also of rubidium. And of course, it's not tunable, but that also means it's not detunable. It's always going to be the right wavelength to excite rubidium atoms here. So along the optical bench, in succession, we have that lamp, collimating lens that captures a decent solid angle and sends a beam all the way through the cell here and eventually to the detector. And then in order, we separate out the even brighter 780 or D2 light by rejecting it with the interference filter. And then the magic combination of a linear polarizer and a quarter wave plate leave in this regime here a circularly polarized beam. So that's where the photons coming in have angular momentum and change the angular momentum projection of the atoms as they polarize or magnetize the sample. And then the magic of optical pumping is that the light that comes through, by its intensity, doesn't matter what the polarization is here, by its intensity is going to give a signal of how much absorption was happening in here, and that's an indication of what state the atoms are in collectively at this stage. So the last step is a collimating lens that refocuses the light onto a photodetector about the same size as the lamp. And that's all there is to it from the atomic point of view. But it is a neat bit of atoms for a source of light, atoms for absorbers of light, and of course the rest of the optics. I emphasize that the lamp here runs at the internal bulb in here happens to run at about 120 Celsius. This actually gets warm, and this is the main power consumption of the system. This heater takes a trifling amount of power, and everything else is done with basically no dissipation and no power investment. The vacuums are permanent. The gas the buffer gas in here is neon, as I recall, and inside the lamp there's a buffer gas of xenon to help the discharge go. But this glass cell and that glass cell are both sealed, no vacuum requirements, no cryogenic requirements, no magnetic shielding requirements, open and tabletop, works like a charm. Then there's a fair amount of attention paid to magnetic field control, and I'll take you through those. The ambient magnetic field here is the Earth's field of about 50 microtesla or something like that. And its direction is north pointing, that is, a compass needle would point that way. But actually the major component of it is downward in our hemisphere. And the first thing we do here with these coils is cancel out the vertical field component. So that leaves only the component in this direction. To avoid having any component perpendicular to this, we just turn the table along the compass heading. So what's left is a magnetic field that is purely along the axis of the beam, and which we can change using these coils, or partial windings of these coils. So for example, the typical thing is to cancel maybe 40 microtesla of vertical field and cancel a residual 10 microtesla of horizontal ambient field, and then you put a slow ramp into these guys to change the total field from, say, 10 microtesla that way through 0 to 10 microtesla that way, and see the response of this light transmission as a function of magnetic field. And this one more thing that comes up later is if you want to drive transitions among the magnetic sublevels of the atoms in here, it turns out you need a oscillating magnetic field and one whose direction is transverse to the optical axis. So these little coils on the ears here of the cell are a pair of non-Helmholtz coils that might run at 20 kilohertz or 5 megahertz or something like that, generating a transverse and oscillatory magnetic field. So that's RF coils here. Radio frequency, for our purposes, extends down into the audio regime, but it can be much higher. Or if you want to do atomic clock type things, you would need for this field to be at gigahertz microwave frequencies, and that's not part of this apparatus, but it could be done. We should entertain questions about this guy, which we'll continue to leave open, but we'll soon transfer to the electronic side of things. So if you have questions about what you're seeing.
What is this?
Yeah, this is a kludge, is the technical name for this. The coils on here provide a transverse RF magnetic field, but talking ahead of time, Peter showed me what I hadn't known before, that there are cases, so-called MX modulation, in which it's nice to have an oscillating radio frequency magnetic field along the direction of the optical axis. So I literally wound a 2-turn coil on each end and connected it up. Another thing not included that could have been in here, everyone talks about the magnetic field at the sample, but the sample is as big as your thumb, and it's not guaranteed by any constitution that the magnetic field will have the same value over that entire volume. So in a real laboratory, especially one in a ferroconcrete building, magnetic field gradients are a problem. That is, the field might be a microtesla or 5 microtesla different here, and that's not a lot of microtesla different over a centimeter, but we can detect nanotesla. So if you were doing this in the research direction or trying to push the limits of this, you would want some coils, gradient coils around this that would cancel out the gradients in the ambient magnetic field. So then you really do have a single value applying over the whole volume of the cell. The nitrogen vacancy center guys never have to talk about gradients because, especially in the one vacancy, single vacancy detection thing, the whole detection system is a nanometer wide, right? So the field has a value there. Oh, and then one more coil we have here. I just wound a little scrap coil on a little scrap form. I'm just using this to energize a DC field, 20 turns at a 20th of an ampere, generate a field in this direction whose field lines come around here. So this is just to put on a calibratable field change over at this location. And you could be more sophisticated, but that's how we did it today.
Sorry,
Yes.
question, why do we need that again? Like, why do we need
Just to
calibrate?
put in, just to make sure it's a live transducer for magnetic field. All right, at 1 part in 500 of its native value. We'll do that by putting a DC current in here, and the field lines coming out of here that pass through the cell here will be detectable. So you might call this a test source or calibration source or something like that. Now it's true that we don't have to do calibration coil design checks. In this case, we have an atomic standard of frequency sensitivity, so we can calculate the field sensitivity from first principles, but it's always nice reality check to have either people bring a magnet into their pocket and see that it's really live, or have a controlled and calibratable stray source of field that you can inject. Okay. More questions about this?
And this is the sensitivity of
Yeah, the photodetector sensitivity there. It turns out for the first experiments we're doing here, we're really detecting rather slow changes in light transmission. So only the, so to speak, DC value of this guy needs to be live. But later on, we might do some things where we modulate the light intensity at 20 kilohertz, and the detector has fast enough response to follow those changes in light intensity, even at that higher frequency.
So where's output for
The output of this detector eventually comes a thin cable here, carries that all the way to here where we process it. So that'll be the intensity monitor for the light.
Okay.
One of the things that people talk about in optical pumping is so-called pumping to transparency. Peter talked about the aligned, the stretch state today, the state where you pump the atoms to their maximum possible L sub angular momentum component, and the sample is, we say, pumped to transparency. And then when you get away from that condition, the sample gets more absorptive and this light level drops, and that's your main diagnostic. In this experiment, because it's not a laser experiment in particular, the intensity drops that we'll see are quite small, a few percent. And I'll show you how small they are in a jiffy. But it turns out, despite the fact you're seeing only small changes in the light intensity, you can still see them with high sensitivity because of basically the stability of the lamp and the detector. And yeah, oh, one more thing. For those of you who are amazed to find that it can be done without a laser, the actual intensity of the beam by the time it gets to the detector here is of order 10 microwatts. And it turns out that's enough power to pump these atoms fast enough compared to the rate at which they relax. So you could do more experiments with more laser power, but quite modest power levels are enough. And I guess you could claim this is incoherent light, right? It's produced by a thermal source. So the light is an amazingly good tool for polarizing the sample and an amazingly good tool for detecting changes in the sample. And one of the hidden leverages in optical pumping is that it'll come to the point where when you drive a transition with this radio frequency magnetic field, say at 37 kilohertz, you can, by the absorption of one photon of that triflingly low energy, you can allow one more photon of visible light to come through. And the photon of visible light has got a frequency of 370 terahertz, 10 to the 11th fold leverage, right? That's why you can detect, that helps to make it make detectable these radio frequency transitions. You're mapping invisibly absorption of radio frequency energy by the atoms into a visibly detectable change in the intensity of the light. So, mighty cool.
What range of in application, practical application?
Rice would be a great topic, but a cell that's 5 millimeter cube is would be considered a big cell in those regimes. I've heard of chip scale atomic clocks where the cell is a few millimeters square and less than a millimeter thick. So here this was not optimized for being small, it was optimized for being big and transparent to the student investigator. Yep.
Is incoherent light advantageous in any way, or is it just simpler to obtain and that's why we are using it?
The main reason for doing it this way is that the lamp type system is cheaper and more stable from a student point of view than a laser system. Laser system either costs a lot of money or has to be locked to stay at the right frequency, whereas the rubidium cell lamp is automatically at the frequency that rubidium atoms can absorb. Yeah. Okay, I think you've seen now the apparatus, and so now let me show you the sorts of signals that can be made to appear. And for simplest signals, we'll take off. Oh, please. I missed that, sorry.
What's the cost for something like this?
I would just want to make sure this is working. That you want to shield against, and that could be done with, not with mu metal, but with conductive shield. But who knows how that's done.
Because of, like, if you pass the vapor
and if there is a heavy magnetic field, it will destroy all the data. So
Oh,
this
yeah.
protects that.
Yeah. All right, good. Okay, so you've seen the beginnings of modulation spectroscopy. That is a way to get out of symmetrical dip, how to get good high precision information about where you are relative to the center of that dip. And that's a technique very widely used in magnetometry, and I think we'll use it in maybe the next schemes that we try. But first I wanted to make sure everybody's up to speed on what we've done so far. Same atomic physics, same magnetic manipulations there, but you might say more sophisticated electronic processing of the same information, namely the light transmission through the apparatus. All right. Observations. Remember that we're parked on a dispersion-shaped signal near its zero crossing, and the signal that we started with, the absorption signal, is one that's a radio frequency resonance at 30 kilohertz. And so you might call this, the student calibration is putting on 50 nanotesla by computation and making sure you can detect that. The faculty level calibration of this is to say, look, if I change this radio frequency from 30 kilohertz to 30.1, that resonant location has to move over. It takes a slightly larger field to spread the levels till they're 30.1 kilohertz apart. And that should change the signal here too. So let me move over 2 digits here and put in 0.1 kilohertz change. Oop, there, that was 0.2. And okay, here's steps of 0.1 kilohertz out of 30 kilohertz. And this is a check that we're in that linear regime of the zero crossing curve. And it calibrates what these step sizes are in frequency units, which don't require any computation about magnetic field strength and all that. They tell you that you've calibrated the system to magnetic fields in reliable units that don't require TeachSpin calculation or current measurement. So there you go. The guys who care about this, of course, are the ones who do long-term monitoring of the Earth's magnetic field. And if we were at a much more northerly location here and measured the ambient magnetic field more carefully, we could actually see, for example, when an aurora is happening, because it would change by parts in 10 to the third or less the ambient magnetic field. And atomic vapor magnetometry is one way to do that kind of absolute high precision, fully calibrated, atomic standard of accuracy, absolute measurement of magnetic fields. Atomic vapor magnetometers have been put on spacecraft, including on missions as far away from the Earth as orbiting Saturn, and they measure magnetic field strength and send back the information, which is a very fancy instrument indeed. Okay.
Yeah, so 30 kilohertz.
All right.
Yeah, yeah.
By all means.
I can stay
Whoa,
here.
somebody's magnetic. All right. Can you make?
Come back here, so hopefully return.
Yeah, all the magnetic stuff in your pocket. Yeah.
When we come back, it was stay, right?
Here's my car keys, exactly as issued by the rental company, and you see this sort of square wave modulation I'm creating.
Yeah.
So that's worth some number of nanotesla as well.
50 now.
Right. Yeah. That's
So
right.
this
So.
can be used in like military, use cases where if you want to find out people are moving, then
Absolutely, yeah.
Yeah, that's right.
So it's like monitoring a perimeter or something like that.
yeah.
That's
I've
right.
seen some of these devices. They do it, but I think this is another use case.
If a car were to pull up outside the building there, this would go berserk. The field changes to be many microtesla. So
There is what?
a car going by.
Oh, there's a car.
Because you got a ton of steel going by, right? Big changes. And the other thing, car is physically large, and so the length scale on which its field perturbations drop off is about car length rather than the inch length or something like that. So yes, it's hard to move a mechanical object very much without this detecting it.
What about a plane crossing over?
Already, and certainly at the research level, the ambient field is a highly time and space dependent and randomly varying object, so you have to get rid of it first.
I have a question. So it can only detect like a metal or humans also.
Anything that will perturb the magnetic field. So anything conductive with currents flowing, or anything that's ferromagnetic, even if it's not magnetized, will affect the ambient field by, say, if I put a big lump of unmagnetized steel here, a bunch of the magnetic field lines get sucked away from there and get pulled into the steel, and then, so yes, you can detect effects like that.
Biomagnetic fields.